Have you ever experimented with throwing or rolling a ball on a rotating plane, such as a merry-go-round? To the outside observer, the ball appears to travel in a straight line, with a slight deflection away from the thrown direction due to the tangential velocity of the rotating plane. However, in the rotating plane, the ball appears to curve in the direction the plane is rotating in. If we think about the Earth as a three-dimensional merry-go-round, we'd expect to see the same wonky behavior as a projectile goes from near the equator, analogous to the outside of our merry-go-round, towards the poles, or the center of our merry-go-round. Now the Earth is spinning about its axis west to east, completing one revolution in 24 hours. A point on the equator thus travels further in a day than a point near the poles. This means a point at the equator has a larger tangential velocity than a point near the poles. For a projectile fired from the North Pole southward, we see that there is a deflection to the west. This is due to the fact that the further south the projectile travels, the increasing difference between the projectile's tangential velocity, which is 0 at the poles, and the tangential velocity at a location closer to the equator increases. This increasing difference causes the projectile to fall behind and deflects it westward. For a projectile fired in the southern hemisphere, the same phenomena can be observed, only the deflection is eastward instead of westward, due to symmetry. Now consider objects in motion near the Earth's surface. If air resistance is negligible, and if there are no forces of propulsion, then the equation of motion follows A, the acceleration of the projectile in the rotating frame, is equal to G minus 2 omega cross v. Integrate this equation term by term once with respect to time. That is, however, the only exact integration. To integrate again, we would need to know r minus r naught as a function of time, which is precisely what we are trying to compute. The recalcitrant term in this equation is already of order omega, however, so we may proceed by successive approximations. First, we integrate our equation for velocity to 0th order in omega to get r minus r naught is equal to v naught t plus 1/2 g t squared plus terms of order omega. We can then substitute this lowest order expression for r minus r naught back into our equation for velocity, and then integrate again to get r minus r naught is equal to v naught t plus 1/2 g t squared minus 2 omega cross 1/2 v naught t squared plus 1/6 g t to the third plus terms of omega squared. Compare the two terms in v naught. We see that the second term is of order omega t times the first term. The same is true for the two terms in g. Thus the expansion is in powers of the dimensionless product omega t. If the flight time is 10 minutes or less, then omega t is going to be less than 4.4 times 10 to the negative 2. The neglected term in our above equation, which is in omega squared, represents a fractional error then of, at most, 10 to the negative 3. We'll now move to a practical application of the Coriolis effect, the Big Bertha calculation. The Big Bertha was a gun used by the Germans in World War I to bomb Paris in 1914. With a muzzle velocity of over 1,400 meters per second, the gun was capable of firing a 106 kilogram shell to an altitude of 42.3 kilometers, the greatest height reached by a human-made projectile until the first successful V-2 flight test in October 1942. In our calculation, we'll neglect air resistance and see whether the range and flight time of the projectile are close to the measured results. We'll denote r, the range of the projectile. Find that r is equal to 202 kilometers. We can now proceed with the time calculation. Right, flight time of 242 seconds. And we can see from this calculation the 242 seconds is much less than the 10 minutes that we solved for in our simplification. If we assume that v naught is in the southward facing direction and plug in our t values for our solution for r minus r naught, we see that r minus r naught is equal to v naught t plus 1/2 g t squared minus omega cross v naught t squared minus 1/3 omega cross g times t to the third. We get two different cross terms, omega cross v naught and omega cross g. These two cross terms will cause the deflection of the projectile, the Coriolis effect. Because we're only interested in the deflection, we'll just analyze the two cross terms. Omega cross v naught t squared minus 1/3 omega cross g t to the third. From the diagram I've drawn, we can see that these equivalent deflections are negative omega v naught sine of 77 degrees times t squared minus 1/3 omega g cosine of 48 degrees times t to the third. Plugging in the angular velocity of the Earth, the acceleration of gravity, the initial velocity of the projectile, and the time it takes for the projectile to land, we get that the deflection westward is 6,000 meters, while the deflection eastward is 2,300 meters. The Coriolis effect thus deflects the projectile 3,700 meters westward. 3,700 meters is equivalent to about 2.3 miles. This is close to the actual deflection that the Germans accounted for. They observed deflections as large as 1.6 miles. So our calculation is within the order of magnitude we're looking for. We'll do one more calculation to show the effects of the Coriolis force. One common misconception associated with the Coriolis effect is that it is responsible for toilets draining opposite directions in the northern and southern hemispheres. Most people watching this video probably know that it is just the geometry and shape of the basin that it causes the water to flow a particular direction. However, now we have the math and knowledge to prove it. Assuming that the water in the bowl has no initial velocity, our equation for r minus r naught, the deflection caused by the Coriolis effect, simplifies to r minus r naught is equal to 1/2 g t squared minus 1/3 omega cross g t to the third. This cross product simplifies to 1/3 omega g cosine of lambda times t to the third, where t is equal to 2h over g to the 1/2. H is just the height of the basin above the ground, and lambda is the latitude. If we plug in the latitudes for one city in the northern hemisphere, say Cleveland, which sits at 41 degrees north, and a city in the southern hemisphere, Wellington, New Zealand, 41 degrees south, we find that although the Coriolis terms deflect in opposite directions, the magnitude of the Coriolis force is only shifts the water 6 microns. This is simply because the time scale we're looking at is just too small. To observe the Coriolis effect, you need large time scales or large velocities.
The Coriolis effect has nothing to do with the direction the water into the bowl goes.
Thank you for watching my video.
Thank you for watching.